Hey guys, Mr. Smith here, and in this lesson we're going to be talking about equivalent trigonometric expressions, which is a fancy way of saying identities. So we'll be reviewing some equivalent trigonometric expressions from your grade 11 course, identities from your grade 11 course, and we'll be learning some new ones. I don't think the lesson should be too long. I know the last one was a little beefier, but this one shouldn't be too bad. In actuality, this is kind of what we're focusing on for the remainder of our unit. All right, sorry, I just had someone come into my office. So yeah, we're talking about identities today. Let's get started. Not even sure if that had any good continuity, but in your grade 11 course, normally towards the end of your trigonometry unit, you learned certain trigonometric expressions were equal, and they were equal no matter what you plugged in for theta. And we called this situation where you have two expressions, trig expressions that are equal, an identity. And it's an equation that's true for all values of the variable, except where one of the sides might be undefined, but it's true for every value of the variable. And there's three main identities you guys learned about in your grade 11 course. So let's just chat about them because we might make use of them. Well, we will make use of them over the course of the next couple of lessons. The first, it's not so much an identity. You guys already know these. It's like just the definitions of our three reciprocal trigonometric ratios that cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. And cotan theta is equal to 1 over tan theta. So these are expressions where the left and right are equal no matter what you plug in for theta, as long as it's not undefined. The quotient identity was something we touched on, and the quotient identity says this: the tan of theta is equal to sine theta divided by cos theta. This is true. You can verify this. You can do if you want to, maybe just do this quickly. Let's do the sine of 24 degrees divided by the cosine of 24 degrees. And then separately do the tan of 24 degrees. And you will see that those two guys are equal. I'll do it too. Sine 24 divided by cosine 24 degrees. I got about 0.4452. Tan 24, same thing. So in your grade 11 course, you would have kind of shown the why of that's true. And it has to do with the unit circle. Sine of an angle corresponds to the y value on the unit circle. Cosine corresponds to the x value. And tangent is the ratio of y over x, which would just give you sine over cosine. The last one is the Pythagorean identity, and it says this. It says that when you square the sine of an angle, another interruption, when you square the sine of an angle and you add it with the square of the cosine of an angle, the same angle, you get 1. And this is true no matter the angle, which is pretty cool. And this comes from the fact that the unit circle has the equation x squared plus y squared equals 1. And the fact that for any point on the unit circle, xy equals cos theta sine theta. So cosine squared plus sine squared is 1, or sine squared plus cosine squared is 1. So you guys, those were the three main ones you learned in grade 11. And then you proved a bunch of other identities using these basic ones. What we're going to do today is we're going to begin looking at identities, some more identities, and today a specific type. We're going to call them co-function identities. And as we work throughout this lesson, we're going to get a table of, by the end, a table of 12 co-function identities that you can just use at your pleasure. Whenever you're doing, working on some problems, you just have a nice set of 12 just to look at and make use of whenever you need. You don't need to memorize them. They'll just be all in a nice one spot. So to motivate our first couple of new identities, I want you guys to evaluate these 8 trig ratios and then see if you can make any connections from what you see. So I have these done already. So I would encourage you, please pause the video and just do these 8. For the final 4, you don't need to do the exact ratios. You can if you want to. I just do them to 4 decimal places. It'll illustrate the point. So yeah, please pause the video, give those a go. All right, I will have assumed you've got your 8 values. Here they are. And what you would have noticed was that each pair, A, B, C, D, E, F, and G, H, gave you the same value for those trig ratios. The sine of 40, same as the cosine of 50. Cosine 53, same as sine 37. Sine pi by 3 and cos pi by 6 give you the same thing, as do cosine pi by 4 and sine pi by 4. And this isn't just a coincidence. Those in A, B, C, D, E, F, and G, H, the 2 angles given are related in some way. So if you haven't figured out the connection, or maybe you just haven't spent some time thinking about it, what is the relationship between the angle measures A, B, C, D, E, F, and G, H? What's the relationship between 40 and 50, 53 and 37, pi by 3 and pi by 6, pi by 4 and pi by 4? Hopefully you've had a chance to do that. You paused the video, gave it a think. But if you noticed, each pair adds up to a specific value. Each pair adds to 90 degrees. Or pi by 2 radians. And this actually motivates our first of 2 of our cofunction identities. The first one says this: the sine of an angle, and I'm going to use x here instead of theta, so the sine of an angle x is equal to the cosine of pi by 2 minus x. The sine of an angle is the same as 90 degrees minus that angle, the cosine of 90 degrees minus that angle. Also, the cosine of angle x is equal to the sine of pi by 2 minus x. So these are the first of our 2 cofunction identities. And you'll see why we call them cofunction identities in just a moment or two. If you would like, you can go populate these 2 guys if you go all the way to the back of our lesson. As we get more and more of these guys today, you can add these. Actually, yeah, you can add these to your note, but they'll be there at the end of the note too. So yeah, don't want to spoil things. Let's get back here. These are our first 2. We just showed them numerically. But let's look at and just try to convince you that these are true. And we're going to look at 2 different ways to illustrate these are true. We're going to focus in now just on the first one: sine x equals cosine pi over 2 minus x. We might have enough space just to verify both. The first is just by using SOHCAHTOA. So here's a right angle triangle. You can see the right angle, pi over 2 radians. We've labeled the angle at A with a little x. And we've got all 3 sides labeled according to how we label triangles: little a across from angle A, little b across from angle B, little c across from angle C. But if I look at, and then if also I want to add in this diagram too, the value of angle C is going to be pi by 2 radians minus whatever x is, or like 90 degrees minus whatever x is, but we're just working in radians here. And so if I look at the sine of angle x in this diagram, well, sine is opposite over hypotenuse. And so the sine of angle x is equal to opposite, which would be A, over hypotenuse, B. And if I look at the cosine of the other angle, pi by 2 minus x, cosine is adjacent over hypotenuse. But guys, look, the adjacent side to that angle, pi by 2 minus x, is also A. It is just what is adjacent to C is the opposite to angle A. And you get A over B. So we've just kind of shown this is true by looking at a right angle triangle. Of course, the same is true for cosine x and sine pi by 2 minus x. But I think that's enough. I don't want to get things too cluttered. Now, just you'll have to know this is actually kind of only illustrates this idea for angles between 0 and pi by 2 radians. Our next method will actually illustrate it for all values of the angle x, and we're going to use transformations. So we look at more detail at the graphs of trigonometric functions in our next unit, but we can actually use transformations to show these cofunction identities, and we're going to do it. We're going to review how to draw the basic sine function, the basic cosine function, and just do some transformations. Won't be too bad. And you know what? This also just gives us a little bit of a head start to reviewing some stuff for our next unit. So to graph the basic sine function, I'll graph the basic sine function on this one. So you guys learned last year, you guys would have made these graphs in degrees. So the sine function started at 0, 0, comes back to 0 every 180 degrees, and reached a maximum of 1 at 90 degrees, and a minimum of -1 at 270 degrees. And then, of course, you realize that just repeats over and over. It's a periodic function, repeats every 360. And so we have this graph of we call the basic sine function. Okay, looks good. The basic cosine function had a central maximum at 0, 1. The cosine of 0 is 1. And then it came back to 0 at 90, reaches a minimum of -1 at 180, back to 0 at 270, and then at 360 again it's 1, and it's periodic every 360. Again, these are graphs you guys would have looked at last year. We'll review them in more detail later on. But for now, we can make these simple sketches. All right. So now let's focus in on, again, we're just focusing on our one identity, that sine x is equal to cosine of pi by 2 minus x. Well, I've got a third graph here, and let's look at this graph. We're going to look at the graph of cosine of pi by 2 minus x. And before I graph it, I'm going to rewrite that a little bit. I'm going to write this as the cosine, and I'm going to take out a negative. And what that's going to do is it's going to turn negative x into positive x. And it's going to turn positive pi by 2 into negative pi by 2. So just take a moment and digest what I just did there. I just kind of manipulated the inside. I factored out the -1 and just reordered the terms. If you expand this out, you get negative x and you get positive pi over 2. So these two expressions are equivalent. But what this is showing, if we review our knowledge of transformations, we did some of that in our first unit. The minus pi over 2 is indicating that the graph is translated to the right, pi over 2 units. And the negative is indicating a reflection. And because it's on the x, it's a reflection in the y-axis. So let's have a look at what this graph looks like. So to start off, I'm going to just do a light sketch, just maybe in one color. I'll just use dashed lines of the basic cosine function. Graph it here. You can just, if you're taking notes, you can just slightly use a pencil, and I'll just dash it in here. So this is the basic cosine function. And I'm going to first apply the reflection. So if you reflect that in the y-axis, the cosine function is actually an even function. And so it'll just look the same. So the reflection taken care of, do that first. And now let's take that graph and let's shift it right by pi by 2 units. Now we know that pi by 2 radians is equivalent to 90 degrees. So let's shift this over 90 degrees and let's see what we get. So all these points are going to move to the right by 90 degrees. So something like that. That gets shifted there and there and there and there, and there'd be a point here. And now I'm going to graph this in green. And this graph should look familiar. This is actually the exact same graph as our basic sine function. So what we have shown is that this graph, cosine of negative x minus pi over 2, is actually equal to the graph of sine x in every way. And so we've shown that identity is true. And this, unlike our initial reasoning in method 1, this is true for any value of x, positive, negative, large angles, whatever. So very interesting. All right, so hopefully you are convinced of those two. Let's talk about some other useful cofunction identities. So these first two, both are of the form pi over 2 minus an angle. We'd like to get other cofunction identities where we have pi by 2 plus another angle. So we're going to look at two graphs here. We're going to graph sine of pi by 2 plus x, and we'll see if we can't figure out another third cofunction identity. And then we're going to graph pi over 2 plus x, a fourth. So things to keep in mind as we graph this, I can rewrite this as the sine of x plus pi over 2. So we're basically just taking our basic sine function and shifting it left 2 units. Now, I'm going to, because we've graphed the basic one a few times so far, I'm just going to do that right away. I'm going to, well, you know what? It doesn't, that's even in the wrong spot. It's not going to take me too long just to do it. So why don't I just do it? Don't be lazy, Andrew. Let's just do it. 90, 180, 270, 360. And I'll dash it in. Dash it in. All right. And while I'm at it, I'm just going to get the cosine one on the other guy filled in. 0, 1, 90, 270, 360. And dash these in. Good enough. All right, let's do these shifts. So we're shifting in our first one, we're shifting that sine function to the left by pi over 2 radians, i.e. we're shifting it left by 90 degrees. So every point moves left 90. Maybe you can see where this is going. Kind of neat how all this works out. Okay, so if I make the graph of sine of x plus pi by 2, I get a familiar looking graph. This is just the graph of the cosine function. It turns out we have a third cofunction identity that involves adding an angle to pi over 2. And it's this, the sine of x plus pi by 2 is just equal to cosine, the cosine of x. That's pretty neat. And that works for all angles. Why don't you try the next one, graph that shifted cosine function, and see if you can create the cofunction identity for that remaining one. So maybe you want to pause the video and give that one a try. Or I'm going to do it right now. You can follow along with me. I'm going to switch back to green. So in the same way, this guy, cosine pi by 2 plus x, is the same as cosine x plus pi by 2. And we're just going to shift our cosine function left. Here, 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 here. Down, up, and down. All right. Now that graph, it's not the sine function or the cosine function, but what it is, it's just the sine function just reflected in the x-axis. It's just the negative sine function. This is the graph of y equals negative sine x. What we have shown is that the cosine of x plus pi over 2 is equal to negative sine x. And these are all things you could just easily verify with a calculator. And that's actually part of some exercises later on. But what we have now are four kind of what I call just like our are basic cofunction identities. And now you can see why they get their name cofunction. It's because the sine and cosine, any sine function, you can write as a cosine function, just a horizontal shift. So they're kind of like cofunctions, cofunction identities. So let's do a little summary. And we are going to get this into a final table at the end of the lesson. So we're just going to have them in multiple spots. That's okay. We're just kind of building up what we have. Excuse me. So we started off with using kind of a right triangle to show that, in our calculators, to show that the sine of an angle x is equal to the cosine of pi by 2 minus x. And we showed that that works for all x. It doesn't just work for acute angles. So that was pretty neat. And that in a similar way, the cosine of an angle is equal to the sine of 90 degrees or pi by 2 radians minus the angle. So we showed that on our calculator, and you maybe even already kind of knew that idea from your grade 10 course, even possibly. And then we just showed two more where instead of it was subtracting an angle from pi by 2, it was adding an angle to pi by 2. So we saw that the sine of x plus pi by 2 radians is actually equal to the cosine of the angle, cosine x, and that cosine of x plus pi by 2 is equal to minus sine x. Now, if you're panicking that you have to memorize all these, nope, you don't have to memorize them. We're going to have them in a nice summary table, and you can draw on these whenever you need. Now, we're going to have 12 by the end of our lesson, and we've already done the heavy lifting, actually. The other 8 just kind of fall out of what we just showed here. If you take the reciprocal of each of these guys, so I'm not sure if I'll write all of these out because you might get the idea. But if I take the reciprocal of this first one, if I take the reciprocal of both sides, then the equation still holds true. But what is 1 over sine x equal to? It's cosecant x. What's 1 over cosine equal to? It's secant of pi by 2 minus x. So this is a fifth. It's a reciprocal cofunction identity. The cosecant of an angle is equal to the secant of pi by 2 minus that same angle. I might show my work for this next one, and then for the final two, I might just maybe as an exercise with you guys, or for you guys, just to try those on your own. So 1 over cosine x equals 1 over the sine of pi by 2 minus x. This gives you that secant of x equals the cosecant of pi by 2 minus x. Okay, and that just comes from taking our basic ones and just flipping them. All right, can you take the final two and take their reciprocals? Now we'll have 8 cofunction identities. You know what? I might just pause my recording here, and you guys can try that, and then I'll show all my work. So yeah, we'll see you guys in a second. All right, guys, and we're back. And yeah, since I paused the video recording, I could just show the rough work. So I thought some of you guys might appreciate that. But now we have 8 cofunction identities. 2, and then the first 4 relating sine and cosine. The second 4 relating cosecant and secant. 2 representing pi by 2 minus an angle. Another representing pi by 2 plus an angle. All right, and for our remaining 4, we're going to use the quotient identity. For our first one, I'm going to take sine x, and I'm going to divide it by cosine x. Now we know from our first basic ones that the sine of x is equal to the cosine of pi by 2 minus x, and that the cosine of x is equal to the sine of pi over 2 minus x. Now, using our quotient identity, sine over cosine is equivalent to tan, and cosine over sine is equivalent to cotan pi over 2 minus x. So in a similar manner, we can do cosine x over sine x. This is equal to the sine of pi over 2 minus x. cosine of pi over 2 minus x. And we get a similar identity relating cotangent and tangent. The cotan of an angle x is equal to the tangent of pi by 2 minus x. And we're going to do the same thing for our remaining two. So I might have you guys try the next two, and I'll pause the video, and then I'll have them ready. And then you can either tweak what you had or confirm what you had. So I'll see you guys in a moment. All right, and we're back. And I've got our final two co-function identities I got by taking our basic ones and looking at the ratio of sine over cosine or cosine over sine. And this kind of completes our list of of all 12 co-function identities. Half of them for pi by 2 minus an angle, half of them for pi by 2 plus an angle. If you want to, right now, you could pause the video, and if you want to have them all summarized, I provided a table for you at the end, and I have them all here as well. I just screen grabbed from the MHR text. Just because the writing's a lot nicer than ours. But these are than mine. These are the 12 identities featuring pi by 2 that we just kind of developed today. And now you just have them all in one spot, and you guys can just use them moving forward. I won't ask you to memorize them. Of course, you have them in your notes and stuff. But it might be reasonable for me to have you explain where they come from, maybe on a unit test or something. So having developed these 12 co-function identities, what can we do with them? We're going to do a few exercises just to get used to the new identities. Yeah, again, it's just to kind of become better at working with radians. We're using these new identities, and it's just good exercises, right? It's not like this kind of thing is going to come up in your applications or on the work site for the rest of your lives, but it's just these are good exercises just to get better and get stronger. So here, we're given that the sine of pi over 5, that's not an exact angle that we know, but it's about 0.5878. We're going to use equivalent trigonometric expressions to evaluate cosine of 3 pi over 10. So we understand that we could just type in cosine 3 pi over 10 and get an answer. It's not the purpose of this exercise. The purpose is to try to play around with these co-function identities. So our job with this question is to, in the strong hint, they give you the value for pi over 5. Can we write 3 pi over 10? And 3 pi over 10 is smaller than pi over 2. Can we write 3 pi over 10 as pi over 2 minus some other angle? Because then I'll be able to use one of our identities. So we are going to do that. Strong hint. They gave us sine pi over 5. Let's see how this works. So we'll just do A on this slide. So I'm just going to make a little note here. I'm just going to say, can I write 3 pi over 10 as pi over 2 minus some angle? I'm going to call that angle little a. Well, I mean, we can, and we can find out what a is just by solving this little equation. So just bringing the a to the left and subtracting 3 pi over 10. A is pi over 2 minus 3 pi over 10. Can I squeeze this in here? Probably. That's 5 pi over 10 minus 3 pi over 10. I'll go up here. That's 2 pi over 10, which is pi over 5. What a coincidence. They actually told us what the sine of pi over 5 was equal to. So we can use one of our co-function identities. Which one are we going to use? Well, we're looking for the cosine of 3 pi over 10. What we just found, let's rewrite that. We just found out that 3 pi over 10 can be written as pi over 2 minus pi over 5. And now we have a co-function identity. It was one of our first ones, remember? The cosine of pi by 2 minus an angle is equivalent to the sine of that angle that we're subtracting, pi by 5. And we know this is equal to 0.5878. We could have punched that in ahead of time, but we're getting experience and practice working and manipulating with these cofunction identities. That's the purpose. The purpose isn't to get the answer, it's to get some experience working with these. And you can check that now if you make sure that you're in radians mode and you do the cosine of 3 pi divided by 10, 0.5878. All right, let's try B. So what you'll notice with B is that 7 pi over 10 is greater than pi over 2. Right? 7/10 is more than 1/2, right? And so we're going to do something similar with B. So what's the wording do I use? Yeah, can we write 7 pi over 10 as some angle, as pi over 2 plus some angle? So can we write 7 pi over 10 as, and I think in our identities we had, I'm just going to be very consistent with our identities. Yeah, we put the x, the angle first. So can we write it as some angle A plus pi over 2? And spoiler alert, we can. We just solve for A. 7 pi over 10 minus pi over 2. Find a common denominator. 7 pi over 10 minus 5 pi over 10. You can see where this is going. We get 2 pi over 10. We get pi over 5. And lucky us, we actually told that the sine of pi over 5, again, is 0.5878. So let's finish this one off. The cosine is 7 pi over 10. We can write that as the cosine of pi over 5 plus pi over 2. And then we can use an appropriate identity. We know that the cosine of an angle plus pi over 2 is equal to the negative of the sine of the angle. This is equal to negative sine pi over 5. And sine pi over 5 is 0.5878. So the cosine of 7 pi over 10 will be negative 0.5878. Again, let's check this out. We can do it on our calculators. The cosine of 7 pi divided by 10. I can show you guys what I got there. Yep, and we verified it. So these kind of questions are great questions just for building up skills, building our strength, getting used to these cofunction identities. Of course, we could just use a calculator, but that's not the point of these questions. All right, we got one more example to do. We're going to kind of do the same thing, but we're going to use one of our reciprocal identities. So we're given here that cosecant of 2 pi by 7 is about 1.2790. Again, we're going to find secant of 3 pi over 14, but not using a calculator. We're going to use our one of our cofunction identities. And the key is, can we write 3 pi over 14 as either pi over 2 minus something or pi over 2 plus something? And 3 pi over 14 or 3 over 14, it's less than a half. So we know we're looking for a pi by 2 minus some angle. So again, can we write 3 pi over 14 as pi over 2 minus some angle A? And we can solve for A. I wonder what it's going to be, given how this question is cooked up. Pi over 2 minus 3 pi over 14. That is 7 pi over 14 minus 3 pi over 14. Go up here. This is 4 pi over 14. And wouldn't you know it, 2 pi over 7 is popping up. So what have we shown? Our goal is to evaluate the secant of 3 pi over 14. We have now shown that this is 3 pi over 14 is equal to pi over 2 minus 2 pi over 7. And we have a co-function identity for this, the secant. And full disclosure, I don't have these memorized. I know that they exist. I know that's related to the cosecant, but I don't remember if it's positive or negative. So I just look it up. The secant of pi by 2 minus x, we know that's cosecant. So it's just plain old equals cosecant of x, or of 2 pi by 7, which is exactly 1.2790. And again, we can check this, and let's check it. So cosecant, so we're finding secant of 3 pi over 14. So let's find the cosine of 3 pi over 14. So for the cosine of 3 pi over 14, I got 0.7818. And then we're going to find the reciprocal of that. So you can use your reciprocal button. You can raise this to the power of -1. You can copy it down and do 1 divided by this number, whatever you prefer. But I got 1.2790, just like I expected. One more time, guys. I know, obviously, we could just use a calculator to evaluate these. Not the point of the exercise. The point of the exercise is to get stronger, get used to these co-function identities a little bit. Yeah. The last thing we'll do, if you weren't quite convinced that some of these were true, you can, in general, if you're not quite convinced any identity is true, or if you want to check, like I know some of your textbook questions that you're going to work on are these two things equal? Is this an identity? This expression equals this expression. Is it always true? Well, one way to check if it's always true without actually doing math or doing some algebra is to graph each one. Now, graphing secant x and cosecant x, we are doing these in our next unit. I don't expect you guys to know what these graphs will look like, but we can punch these into a program like Desmos and see if they give us the same graph. So that's what we're going to do. So I have Desmos, I think, queued up somewhere here. I have a lot of things open. We'll just go here and just load up Desmos. Thought I had it queued open. No problem. So yeah, let's graph it. Now, here's one thing: when we're graphing trig functions, we want to make sure that our x-axis is in radians. So if you're using Desmos like me, you want to go to your settings, and you want to make sure that you're on radians. So depending on what you've been doing in the past, you might be set in degrees. You want to make sure we're in radians. So let's sketch these guys. So we're looking to so it's secant is our first graph. So we're going to graph I'll just say y equals the secant of x. That is a cool graph, I got to say. Where that graph comes from, is a part of our 5th unit. We're going to make use of the fact that we've already worked with reciprocal functions. Like we've done reciprocal of a linear function and reciprocal of a quadratic function. Well, then we're going to do reciprocal of periodic functions. It's going to be a lot of fun. But that's the graph of secant x. And I'll add a new one here. And our second guy is cosecant of pi by 2 minus x. So cosecant of, and then I think I'm going to get do I have a pi button here? Yeah. Pi divided by 2 minus x. Okay, so very similar. And if I have both at the same time, we can see that they are just overlapping each other. So that's pretty neat. So you can verify any identity by using graphing technology. That's pretty cool. So I hope you enjoyed that lesson. So we took our identities to the next level. We reviewed some identities from our grade 11 course, talked about where they come from, and then we saw some new identities. We called them co-function identities. We have 12 of them. Half involve they all involve pi by 2. Half involve pi by 2 minus an acute angle. Half involve pi by 2 plus. And if you want to summarize these in your notes, then you just have a nice place to come look at them. All right, next up, we're going to look at more identities that can be useful for, especially when you get into some later level university courses. You guys got to believe we're not just giving you guys identities because we're mean and we like to make you guys feel pain. No, identities can actually be very, very, very useful. Um, but we're not quite there yet for you guys to see the usefulness. But yeah, next lesson we're going to look at some other really cool identities, and I'm looking forward to it. Until then, got some suggested practice for you guys. As usual, do as much as you feel that you need to in order to get comfortable. And you know, when you have a lot of questions assigned, you have the flexibility. If your questions are repetitive, you get the idea, then just do 1 out of 4, 2 out of 4, or whatever you need to do, right? Okay. Well, hope you guys are doing well. I enjoyed giving that lesson. Hopefully, you guys enjoyed doing it. Take care, guys. Stay well. We'll see you soon.